All right, you guys good? You see, we're good. I need to get you guys on the side here so I can see you all. There we go. All right. So I'm going to start by just saying this is the last section. I've kind of condensed this chapter into a couple of topics. We went over fluids. This is kind of the part where I'm supposed to spend a lot of time talking about solids. But I'm not going to spend too much time talking about solids. I'm going to talk about what fluids and solids can do. And one of those things that we're going to look at is called thermal expansion. So, in general, the idea of thermal means kind of heat, expansion, get bigger. We're going to talk about what kind of things do these things when they're heated and just to what degree they do. And I'll show you guys a couple demonstrations today as well. Like I said, without being in the class, it's going to be kind of tough, but we'll figure it out. All right. So we'll start with when things freeze. Most things will contract when they freeze. Okay. So most things actually get smaller when they get colder and freeze. And so what this means is that most things are most dense in their solid state. So if you guys remember back in Mrs. McCarville, density is equal to mass over volume. Basically, the idea is this number, if this number gets smaller, then that number gets bigger. So in general, most things are most dense in their solid state. Now, the one exception, or who's the freak? Well, there are actually quite a few exceptions, but there's really only one that we care about, and life as we know it would be way different if this wasn't the case. The one exception is that water. Water tends to get less dense when it freezes. It is one of the exceptions. There's some other exceptions. I believe gallium's this way, and there's some other things that we don't care about. Water is most dense at 4 degrees Celsius. So like if you have a lake, it is going to be colder at the bottom of the lake than it will at the top of the lake because the cold water sinks. But when the water decides to freeze, it has this weird density inversion, and it actually expands, and that has to do with the shape of the water molecules. So water is really not what we're talking about today. So I wanted to kind of start with that and just get that out there. We're really not worried about water a heck of a lot. What we are worried about is pretty much everything else on this chart I'm going to give you. So thermal expansion, the idea is this: most things expand when they're heated. So if you heat things up, most things will expand. Actually, water does this as well. So water is a real weirdo. It's just so weird, where it has a point where it's a solid, it's less dense than the liquid, but the gas is obviously less dense than the liquid. So water is just kind of a freak. So when you heat things up and they expand, what happens is it causes their density to decrease. So once again, density is equal to mass over volume. If I heat something up and that number gets bigger, then that means that number is going to get smaller. And we experience this in lots of different things in our world. Most notably with fluids is air. Hot air tends to rise, cold air tends to sink. Or with liquids, and things that are kind of in the liquid state, think of like a lava lamp. So the movement of those things, when you have this temperature inversion, this density change, causes these things called convection cycles. So this is the idea of hot air rising and cold air sinks. So usually there's some form of heat source, and what happens is that the air that's close to that heat source will expand, and it rises up and it gets away from this heat source. And as it gets away from the heat source, it cools and it becomes more dense, and it creates these weird little cycles. And like these things can happen in your house, or if you look at the big picture, it can happen on the globe. This is why, just meteorology and the idea behind air, the global winds kind of drive where our climates, why our climates are the way they are. There's lots of other factors associated with that, but that's kind of the idea. So that's convection of air, hot air rising, cold air sinks. Convection of water, same idea. So cold water will sink and warm water will rise. Think of it this way: if you're cooking your mac and cheese, you're heating some water up, this water is going to start circulating and making a convection cycle. Okay, so that's not really what we're going to look at a heck of a lot today with thermal expansion. We're actually going to look and focus more on solids and the degree by which they do expand. So solids will also expand when they're heated. And, if you are an engineer or going to be an engineer, especially like a civil engineer, which is somebody that I guess designs kind of towns and like things like roads and that business, think of some problems that this can cause. So solids that heat and contract, or heat and expand and cool and contract, this is going to sound stupid. A bridge in the summer is longer than it is in the winter. Like, what? What are you talking about? Yeah, that's the case, man. Things tend to expand. Now, do they expand 3 to 4 to 5 feet? No, they don't, but they expand enough where if you don't plan for this, you're going to have a broken bridge. You're going to have a big mess, okay? So what we're going to do is we'll look at how solids tend to expand. So a couple demonstrations for you here real quick. These things are brass. So I don't know if you guys can see this. This brass ball can go through this brass hoop. And if let's see here, heat this up with the Bunsen burner, I'm going to get it going here. Right, like I said, sorry, this isn't ideal. I'm going to heat it for about 20 seconds or so. Maybe 25. What happens is that this brass will expand to the point where it will not be able to leave the little hoop here. So if we pull that, it won't go to the point. I don't know what I'm going to do with this now that it's like super freaking hot. That was genius. I'm going to throw some water on it in the sink. It's going to make a big mess, okay? This will be a little easier for you to see. So this is called a bimetallic strip. This just looks like a little piece of metal. But what it actually has is two different types of metals. It has a type of metal, very thin strip on the top, and a very thin strip on the bottom. And these two metals do not expand at the same amount. So as if they're heated in the same way, one of them will expand more than the other. And so now the strip looks kind of straight, but if I heat it up real quick, what happens is one of the sides will expand faster than the other side. So it curves it. Now, obviously I could have went over there and just bent to myself, but that's not happening. So as this thing cools, it will eventually straighten out. So the top layer here expanded more than the bottom layer, and that's why it is curling down. Okay, it's bimetallic strip. Thermostats, old school thermostats usually have these things coiled inside, ones that are not digital or electronic, and that's how the thermostats, old school thermostats, kick on, is with one of these bimetallic strips. It expands, contracts, and it kicks on the furnace or whatever. Okay, so what we're going to do is look at the degree of how much these things expand when they're heated. So like I said, on Classroom, I shared a chart with you that has the relative amount of how much these things heated or expand when they're heated. It is, the chart's going to look a little silly because the numbers look really weird. Okay, and I'll explain why they're doing that and making the numbers look really weird. Okay, so the table of coefficients, I'm going to just go ahead and flip the slide here. Like I said, you have this in Classroom. I don't know if you guys can see that, but here we have some solids. Here we have steel that's handwritten by a former student. Yes, I told them to do that in their book. There are two ways in which things can expand for us. The first way is just looking at something in one dimension, linear expansion, okay? And then the second way is looking at how much the volume expands. So not in just one dimensions, but three dimensions. So when you look at these numbers, you're going to notice they look really weird, right? Like everything here is times 10 to the sixth power. So all these solids here have linear coefficients. Does it make sense to you why? And everybody's muted, so you don't even have to answer. But hopefully it makes sense to you why a liquid would not have a linear expansion coefficient. Why with liquids we care actually more about volume expansion. Hopefully that makes sense to you. It's tough to find the length of water or whatever, right? But it's easier to find the volume of that because it takes the shape of its container. So here we have linear coefficients. Here we have volume coefficients. What I want you to notice, all of these are written to the power of times 10 to the negative 6. The reason they did these is because these are all dumb numbers, okay? These are all really small numbers. Putting them all in the power of times 10 to the negative 6 allows you to compare different things. So in general, the bigger the number is, the more expansion you would expect to see. Okay? The bigger the number, the more expansion you would expect to see. So, for example, aluminum would expand more than oven-proof glass. So notice that glass, you have soft glass, you have oven-proof glass. Oven-proof glass, you don't want to expand that much. If you're cooking something like a casserole in an oven-proof glass, they usually call that borosilicate, or it has the trade name Pyrex. Basically, the idea is you don't want that glass to expand too much and contract a bunch, because if it does expand or contract, what's going to happen is it's going to break. It's going to shatter into lots of pieces. So why we don't take really, really hot pieces of glass and cool them very quickly? Because when they contract, the forces are sometimes so great it causes them to shatter. Okay? So those are the coefficients that we are going to use and that you have posted in classrooms. So you'll notice that little lowercase letter there, that is an alpha, and that letter right there is a beta. So alpha goes with linear expansion, beta goes with volume expansion. Okay? So you need a couple of equations to use these things. I'm going to flip the slide and show you the two equations. So for linear, I'm going to actually rewrite this because I don't know, writing fractions, typing fractions on a board is a little bit weird, all right? So I'm going to just go ahead and rewrite this for you so you guys can make sure you have that, all right? Yep, that's Jesus fish. That's equal to delta L over Li delta T. So we'll kind of unpack this and figure out what this stuff means. Delta anything means final minus initial. So this delta L is actually the final length minus the initial length. Final length minus initial length. Li is the initial length, and delta T is final temperature minus initial temperature. These delta T's can be in Celsius or Kelvin. Either one doesn't matter. Because when you find this difference in Celsius or Kelvin, the number turns out it's the exact same. Okay? So those coefficients are equal to this equation. So if we're doing problems with these coefficients, what you would do is you would look up and you'd have to pay attention to what the material is. Let's say it's aluminum. For this point right here, we would type in 25 times 10 to the negative 6. I think that's aluminum. If it's not, holler at me. And then you would set it up. You're going to find delta L, or maybe you want to find LF. What's the final length? I don't know. Something along those lines. Okay? That's linear expansion. Volume expansion is the other one. Beta, it's going to look exactly the same. So except for instead of length, we're more focused on volume. So delta V over VI, delta T, that's an equation that you guys will use here. So you have to pay attention to, do they care about the length? Do they care about the volume? They care about the length, use alpha. They care about the volume, use beta. That's basically the idea for thermal expansion. Okay, so make sure you get those equations down. And I'm going to pose some problems today that involve these guys. So remember, delta anything is final minus initial. So pay attention. Am I finding the change in volume, or am I finding the final volume? It'd be two different things that you'd have to solve for there. All right, what questions do you have? Because that's kind of all I have there for this stuff. Like I said, I'm trying to condense this. I'll probably give you 5 or so problems today on Classroom. I see no pictures and everybody's muted, so that's sweet. It's all good. I understand.
Looks good to me, Mr. Shaw.
Oh, Sophie's here. The 7th hour represent.
Let's go.
Let's go. Let's see. Sophie, you are you the only one from?
No, and Alexa.
Alexa's here. Yes, that's what we said. We said Alexa and Sophie are the people from 7th hour that are going to represent. So good job.
Oh. Thanks, guys.
Good job, guys. So that's all I have. If you have issues or questions on this, I have office hours at 10 o'clock. You can also email me as well. I'll have office hours next week as well on Tuesday at 10 o'clock. This assignment will not be due until Tuesday at midnight or whatever. So I feel I'm probably going to post 2 assignments this week, and I'm going to have them both due at midnight.
No, I am.
Okay?
Right.
Okay.
That means I'm doing it Tuesday.
Yeah, that's fine. That's fine with me, man. I don't care. Just get it done. You know how many people have not made paper airplanes? It's unbelievable.
That was the easiest.
It's unbelievable.
Okay, Mr. Shaw.
I asked Nathan to do it, and he said no.
Nathan. What's up, Soph?
Okay, I watched like a 5-minute video for each of them on how to make like the world record airplane and glider. And they turned out so bad. So why? Was it the wind, or was it just
Yes.
me?
Normally when they do those world record things, they have a controlled environment. So the air's not turbulent. You know what I'm saying?
Oh, okay.
So like if we were in school, here's what we would have done. We would have built both, and we would have tested them, one for the longest flight, which is usually your small ones with the skinny wings because you can throw them hard. And then we would test one for timed flight, which is usually your glider. You throw it up in the air, and then it slowly circles down. That's kind of the idea. Typically, smaller wings, you have to throw harder, which allows you to like put more oomph into them. Bigger wings, you don't have to throw as hard because there's too much lift if you do. It goes whoop. Okay, there you go. That was our goal, but we're doing this outside and on video. So, okay, I'm gonna hit stop on the record, but I'm just gonna stay here just because